For a while now, we've been studying what we call linear relationships. We started with situations and we graphed their equations, and then we recently talked about what a line really is, which is that it's an equation that describes a relationship between two quantities, and the points that are on that line are the numbers that fit into that equation. But we're going to continue to dig deeper into a line and specifically talk about what is a linear relationship. And to really understand a linear relationship involves how one quantity is changing compared to the other. And that involves us talking about what is called the rate of change, or for a line, that's called the slope. So for any 2 points on a line, there's always going to be, you're moving from one point to another, there's always going to be a vertical change compared to a horizontal change. And if you compare those two values, vertical change or dependent change, to the horizontal change, which is the independent change, we're going to see that that is the same ratio. So for example, if the horizontal change was 1 and the vertical change was 5, you would have a 5/1 ratio. That tells you that the dependent is changing by 5 as the horizontal changes by 1. Now, that's called the slope of a line. There's lots of different rates of changes, but we're looking at a line. So if you looked at these two segments A and B and you were comparing the horizontal and vertical change, you might see that in segment A there's a much bigger vertical change, but there's actually also a much bigger horizontal change. So what it really means to be linear is that when you look at the rate of change, it's consistent as a fraction, as a ratio, as dependent compared to the size of the independent. They're always the same. So that if this vertical change was 5 and this horizontal change was 1, even though obviously that doesn't look like it's drawn to scale, this vertical change might be 10 and this horizontal change might be 2. They're the same ratio. 10/2 is the same as 5/1. And that's what it means to be linear. So in this video, we're going to dig a little deeper into that idea of the rate of change or slope for a line. And we're going to look at how to find that slope, not only from the equation like we've already seen, but also from a picture of the equation, that is its graph, or even more removed, looking at it from its maybe a table of its inputs and outputs, or even if we just look at 2 points that are going to be on the line. And then we're going to talk about how to look at the idea of that rate of change or slope as a unit rate or rate per one. So imagine we had some sort of linear situation that looked like this. Maybe we were charting the amount of t-shirts that we'd sold to the amount of profit that we've made. So we've got 2 points on this line, 10.15, that would mean 10 t-shirts and $15 in profit. And then 32.70, so 32 t-shirts and $70 in profit. So if I ask for the rate of change, how the dollars are changing compared to the t-shirts, we're going to need to figure that out. So first of all, the slope, as a reminder, is the vertical change compared to the horizontal change. And if I tried to do this sort of intuitively, I would try to use the graph grid. But you'll notice that those grids are counting by tens, and I can't really just count individual grid lines. I can't count my way over. But what I could realize is that 10 is that I've sold 10 t-shirts, and the 32 is basically aligned over here at that point on the x-axis, and I could figure out that that change was a change of 22. And I'm going to actually draw that up here on the graph. That is a change of 22 t-shirts. So we've sold 22 more t-shirts. So what impact has that had on the vertical? Well, that 15 means that we are at $15 of profit, and the 70 means that we're at $70 of profit. So if I looked at the rate of change vertically, I could sort of use those numbers and maybe do a little counting and say, hey, my total vertical change here is from 15 up to 70, that's 55. And so if I was writing my slope or my rate of change, that is an increase of $55, as in I've increased by $22 shirts. And that is my slope or my rate of change. And somebody who's really astute might recognize that 11 goes into both of those. And so therefore we might say that is $5 for every 2 t-shirts, because 55 over 22 reduces down to 5 per 2. And somebody that's even more astute might recognize, well, that's the same as $2.50 for every one shirt. And so there's lots of different ways, different numbers that I can use, but these all are the exact same ratio or comparison of dollars to shirts. And this one right here, the last one, is called the unit rate. The rate per one shirt. So where are all the places that we do see slope or the rate of change? First of all, we know that if an equation is written in slope-intercept form, we can see the slope right there. It's kind of slapping us in the face, 1/2. And it's being multiplied by x because we're doing that 1/2 over and over and over again. And so for this line, we know it has a y-intercept of 0. And we would go ahead and plot its slope. So the way we've been doing that so far is essentially to identify some points on that line. You could make those points by making a table, that is putting in the x and then calculating the y. So for example, if you put in 2, 1/2 of 2 gives you 1. And likewise for those other points. Another way we could do it is start at 0 and simply plot your rate of change. As x goes up by 2, y goes up by 1, right? And that is what it means to be a line. It has a constant rate of change. However, there's another rate that's sort of inside of there that we would often miss, which is this rate, the point that's right in between those. For that rate, your x change is 1 compared to your y change being 1/2. So if you were writing your rate of change and you were comparing it as 1/2 to 1, or 1 to 2, change in y to change in x, another way to look at it is to try to make your change in x be 1. And this, when your change of x in 1, that is called your unit rate. So if I was like graphing somebody doing homework problems and figuring out that it was one problem every 2 minutes, I might say that they do 1/2 of a problem in every 1 minute. And that's their rate of working on their homework. They're getting 1/2 of a problem done every 1 minute. Or one problem every 2 minutes, right? It's the idea that there's a ratio here. So let's look at the same problem with slightly more depth and more mathematical insight this time. So first of all, we defined the slope as the vertical change compared to the horizontal change. The vertical change is always going to be on the y-axis, so we're going to call that the change in y. That little triangle is a Greek letter that means simply change in. And the horizontal change would be our change in x. So our change in y compared to our change in x. If we look at the y-axis, it was not really that terribly hard for us to see that we ended at 70 but started at 15. So we could count up from 15 to 70 pretty quickly to figure out that's 55. The numbers are convenient enough in this problem to do it. But somebody who's really astute mathematically would recognize that that increase there would be 70 minus 15. That's called the difference. So how far is it from 15 up to 70? That's really a subtraction problem. So the change in y would be the ending 70 minus the beginning 15. That's not too bad. Likewise, we could do the exact same thing along the x-axis. It wasn't hard for us to count from 10 to 32 and know that that's a difference of 22, but a little bit more mathematical depth would tell us that 32 minus 10, or final minus initial, is going to give us the change overall. So 32 minus 10 is going to be the 22 that we got for our rate of change. Now, somebody who's looking even closer at this problem would recognize that the 70 and the 32 were coming from this problem up here. And the 15 and the 10 were coming from this problem down here. So if we go back and remove all of the detail of this problem, that is, remove the kind of tangible graph that we have in front of us, we could boil it down to really this. 2 points, 10/15 and 32/70. And I was trying to find the change in y and the change in x. So the strategy I'm going to suggest is for us to subtract them, but if you write it like this, it's really hard for people to follow perfectly. So what I'm going to suggest you do is simply take 1 point and write it directly underneath the other one. That way you can see the y's together and the x's together, so we can find our change really, really, really easy. So we're going to call this stack and subtract. And all you do, so easy, is you simply stack those two y numbers on each other. So your change in y is going to be 70 minus 15. You've stacked them, and now you're going to subtract them. And then likewise, we'll do the same thing here. That's going to be our change in x, and that's going to be 32 minus 10. And when I go ahead and actually do that division, I'm going to end up with my 55 over 22, which reduces down to 5 over 2. So this would be what I would call my slope. Try to write that fraction in as simplified form as possible. So let's look at slope in one last way, all the different ways we can see it. We're already familiar with seeing slope in an equation. And when you see a 2 here, that really means 2 over 1. So in that case, our change in y is 2, change in x is 1. So we know how to see it in an equation. Now let's look at it in a table, which is really very much like the 2 points idea. So one of the ways we started to make a table was to just plug in different values of x. So let's say I put in x as 0. That would be 3 plus 2 times 0. That gives me 3. So there's going to give me my y value. We'll let x be 1. Then it becomes 3 plus 2 times 1, which in this case is 5. So put in 1, get out 5. Put in, let's go 3. Okay, so 3 plus 2 times 3. In that case, we get 9. So if I put in 3, I get out 9. And let's look at then our rate of change here. So if I look at this, the change in y would be these numbers over here. The change in y is to go up by 2. If this is dollars, I'm increasing by $2. And then my change in x might be like my shirts again. That would be a change in by 1. So if I look at that as a rate of change, it's the change in y plus 2 compared to the change in x plus 1. I can see the slope or the rate of change in the table if I look at the differences. That's again where I'm basically kind of subtracting. So again, if I look at it this way, from going from 5 to 9, I could kind of count on, or I could subtract 9 minus 5. That shows me an increase by 4. And if I look at the same thing in the x, there's an increase by 2. So if I compare those, here are my rates of change. Change in y, in one case it was plus 2, in the other case it was plus 4. Change in x. My change in x in one case was plus 1, and in my other case was plus 2. But here's the thing about a line. The rate of change is equal, so it doesn't matter whether it's big numbers or small numbers, it's the comparison. 4 over 2 is the same as 2 over 1. And you can see it as a fraction, you can see it from the equation, or you can see it in a table, or you could actually look at the graph and simply say, oh yeah, here was my point here at 0, 3, and as x went up by 1, y responded by going up by 2. Or moving on from there, as I went up by 2, there's the plus 2, my y responded by going up twice that much, 4.